Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is MOHAMAD. I'm going to present my final year project on understanding biomass value change and the environment, food, energy, water nexus in biorefinery using optimization model. This project is under supervision by Professor Madya Dr. Wan Azana and Wan Abdul Karim. So this is the outline that I'm going to discuss. Introduction. What is the biomass value change? So, biomass is a low carbon renewable energy source that can be used directly in an energy application, such as heat and electricity, and can be processed or converted into solid, liquid, and gaseous fuel for different practical applications. So, 94% of all farm sector, the largest contributor of biomass in Malaysia, the equivalent to 157 million tons of biomass generated. So these are the three biomass that I'm going to discuss in my project: the empty fruit branch, mesocat fiber, palm kernel, and shell. So integrated biorefinery integrate biomass conversion process to produce fuel, power, and chemical, and identify the potential pathway for the production of sustainable energy as well as valuable product. Design the palm oil-based integrated biorefinery. So optimization model. So this optimization is a step to systematically identify the alternative reaction pathway prior to the analyzing and ranking the alternative. So this optimization model is adapted by process graph, that is a P graph, in evaluation of the sustainability processes. So the technology that I use in this project and stimulate of biomass conversion, gasification, direct combustion in boiler, and pyrolysis. So the problem statement. The problem of the palm oil-based integrated biorefinery is stated as follows. All sources are sent to a set of biomass conversion technology. The technology convert the sources to the intermediate product. So the intermediate product can be further converted to end product via final conversion technology. So secondly, dictate the overall economic performance of the synthesized palm oil-based integrated biorefinery by keeping the environmental impact at a minimum. Thirdly, specify the potential factor of any environmental impact that is computed at the basis of per unit end product. That is the fraction conversion of source per technology. So determine the total potential environmental impact score, which is to capture the carbon dioxide emission per technology. So adapted the benefits of process graph, that is a P graph, to trade off between the optimization objective, like I said earlier, to maximize the economic performance and minimize the environmental impact. So the objective of my project to examining the many different feasibility pathways for producing energy and high products from biomass, which is a PKS, EFP, and BMF, that also maintain the balance in NEXUS, which is the environmental secondly, to analyze the economic performance and the environmental impact of the palm oil-based integrated biorefinery. Thirdly, to determine the impact of cost and price fluctuation on the economic performance and sensitivity in profit. So this is a methodology. These are the procedure of the palm-based supply network synthesis by the P-Graph Studio. So the following are the steps for the generation of the feasible process flow sheet for the farm base of the under consideration by deploying process network synthesis through thermal pathway for optimal integration of the sustainable technologies in farm-based conversion. So firstly, identification of the material and stream. So this step produces the specification for the inputs and output from the system. So insert all the material uh, and uh, product. So identification of the operating unit. So this study was carried by inserting the required information of the operating unit, such as technologies used in the model. Like I said earlier, the technology that I use in this case study is the gasification, pyrolysis, and the boiler. So we have to input that I have to input the annual capital cost for the technology, biomass, and the utilities amount required and conversion ratio of the intermediate product. So maximum superstructure and generation. This step was produced for ensure the consistency of the resulting superstructure and solution network. A superstructure of the problem was implemented in the process graph and optimization of the superstructure. This result, the result of the solution structure generation produced from the previous step is then proceed performing in the selection of the optimal network by using the algorithm allow optimal process network to be designed based on the solution structure. So this step produce the, the best potential pathway of the palm oil-based integrated biorefinery. So this step we can stimulate and we can play around with the carbon to capture the carbon footprint and play around with the demands and the prices. So until we proceed to the next step, which is the optimal biomass supply chain network. So this is the general superstructure diagram for the biorefinery that this the process that I use in the big graph. So starting from the raw material, EFB, BKS, and EMF, and through technology, which is boiler, pyrolysis, and gasifier, and the intermediate product is the high pressure steam, syngas, and biofuel. Biofuel is considered as the end product. So this intermediate product is going through another process. Is through via the technology conversion technology, which is a steam turbine and a Fischer strokes. So that and this intermediate product is converted into the end product, which is a medium pressure steam, electricity, bio oil, biochar, and biogasoline. So this is the superstructure of the model in the process graph that I convert, that I sketch from the previous diagram. So this is how it's look in the process graph. Uh, so result and discussion. So from the pre-graph, like I showed earlier, this is the best time potential pathway of the palm oil-based integrated biorefinery. After I run and after I stimulate the program, the software. So this is the 10 the best potential pathway. So these show that this feasible structure is sorted according to the profit. So the highest profit would be the structure 1 and following by structure 2, 3 until 10. So, so the highest profit in here, we can see that 28 million and followed by 27 million. So this is a column where I design and I analyze from the feasible structure from the best 10 pathway that I play around with the scenario where I design for the maximum economic performance. So the feasible structure 1 was maximized with the proposed model and optimal solution was obtained. So the maximum economic performance of the selected pathway is the estimate to be 28 million per year. Based on the table 4 that I showed earlier, the total potential environmental impact was computed as 9,000 ton per year. So the preliminary network for the for the pump oil based integrated refinery for this scenario is portrayed in this diagram, like that EFB, BMF, and the PKS uh, were gone through the process of the gasification, and the gasification process was selected in this scenario because of the gasification process produced the high yield of the profit, and the pump kernel shell also selected uh, through the boiler to produce the MPS and electricity. For the scenario 2, design for the minimum environmental impact, which means from among the solution structure, just the from among the feasible pathway, which pathway produce the minimum carbon dioxide emissions. So in this scenario, the optimization objectives, uh, the model was minimized and subject to the constraint as optimal solution was obtained. So the solution structure was determined and the academic performance is estimated to be 25.9 million, while the environmental impact was determined as 5,000 ton per year, which means the carbon dioxide emission. So the feasible structure 16 showing the network design of the pump oil based integrated biorefinery for this scenario. Because in this scenario, the pump kernel shell was being utilized through pyrolysis process, yield bio-oil and biochar as shown in the primary network design of the scenario 2. So for the scenario 3, design for the trade-off between maximum economic performance and minimum environmental impact. So as you can see, scenario 1 and 2 have evidently shown that the competing behavior of the economic performance and the environmental impact in relation to each other. When EP is a maximize, the high score of the EI, the environmental impact is obtained for the scenario 1. For meanwhile, as shown in the scenario 2, when environmental impact is minimized, the relatively lower environmental performance is achieved. In order to address the two optimization objectives simultaneously, process graph, that is a P graph, is adapted in this scenario. The predefined optimized goal to the upper and the lower limit of the multiple objective function were first defined before the model was able to optimize. Scenario 1 provided for the upper limit, whereas the lower limit defined by the scenario 2 as summarized in uh, this preliminary network design for the scenario 3. So the following proposed optimization model was maximized and determined an environmental impact for this scenario 8,000 ton per year, which correspond to the economic performance, uh, which estimated to be 27 million per year. In this scenario, palm mesocap fiber and the palm kernel shell was split between two process units, which are gasification and pyrolysis, and a total of four main products: biochar, biofuel, bio-oil, and biogasoline were produced from the biomass. So, as a given same basis in a scenario 1 and 2, the main product flow rate were determined in this scenario 120 ton per year, 4,000 ton per year, 240 ton per year, and 8,800 ton per year respectively. In this scenario, it is noted that all the empty fruit branch was supplied to a gasification unit similar to the scenario 1 for the production of the biofuel, biogasoline, and syngas. There was no energy generated in this scenario as no biomass feedstock undergo process in the boiler unit. This also indirectly, the emission of the carbon dioxide can be reduced that can potentially increase the environmental impact. So this is the summary of the scenarios that I tagged that recorded in this table. So as you can see, the scenario 1 estimated and recorded 28,000, but the environmental impact ton per year, that is 9,000. So that the main product produced in this pathway, biofuel, biogasoline, electricity, and the medium pressure steam. So as you can see for the scenario 2, the economic performance, or I can say that the profit per year estimated and recorded 25,000, but the environmental impact uh, was determined 4,000 ton per year. For, like I said earlier, scenario 1 maximize the environmental impact. For scenario 2, minimize the environmental impact. But for the scenario 3, a trade-off between the the maximum economic performance and minimum environmental impact. So and this scenario 3 is estimated that the economic performance uh, obtained was 27 million, but the environmental impact uh, 8,000 ton per year that produce four different high value product: biochar, biofuel, bio-oil, and biogasoline. This is the reason why the scenario 3 was selected as the best pathway in this scenario. So this is the graph. Uh, this is the graph that after This is the graph, the optimization result on the Pareto curve. To further analyze the optimality of the result obtained, the Pareto optimality analysis was performed in this work. So the design model was solved by the setting an incremental value for each of the two objective functions by maximizing EP while minimizing the environmental impact to generate a Pareto curve. As you can see here, the graph, the optimal solution, environmental impact versus economic performance. So the graph shows the technology is clean enough. So in this work, a sensitivity analysis was performed to determine the changes in economic performance of the synthesized network as a consequence of the fluctuation in cost of biomass stock and price of product at the rate of the 10% based on the scenario 1. So the result of the sensitivity analysis are tabulated in this table, while the sensitivity graph for the biomass stock and the product were shown in this uh, graph. So back to here. So the 10% fluctuation in the price of the biomass feedstock impose slight impact on the EP environmental analysis in the range of the 0.2%, where environmental performance increase as the cost of the biomass feedstock reduce. Note that also that the cost of the empty fruit bunch ERB and the PMF have the minimal impact on the environmental performance on the economic performance due to their low production in the palm oil mill. You can see from here the 0.03% and PMF 0.05%. So besides 0.2% fluctuation on the EP was observed as the cost of the PKS fluctuate in the range of 10% on the 10%. In this case study, the cost of the PKS was seen to have the highest impact on the economic performance. That is 0.2%. So on the other hand, the largest impact on the overall feasibility of the palm oil-based integrated biorefinery was the price of the biogasoline. A 10% increase in the biogasoline price contributed to the 8.77% increase the economic performance. Meanwhile, the product portfolio changed to produce more of the syngas, which is directly proportional to the production of the biogasoline, because the biogasoline is a product from the gasification process. Note that a decrease in the biogasoline price caused a higher flow rate of the biomass to be sent to the boiler and produce more energy such as electricity and steam in order to maximize the economic performance. It is seen that the 10% decrease in the price of the biogas reduced the economic performance by the negative 8.77%, as you can see from this graph. So the price of the biogasoline played an important role in determining the overall economic feasibility of the palm oil-based biorefinery. Moreover, it's noted that biochar has a no significant effect on the economic performance, which is a 0.27%, as there is no fluctuation in the range of the 10% seen in the price of the product. So the conclusion here, a novel application of the systematic optimization approach of the palm oil-based integrated biorefinery by process graph is presented. So the process graph is adapted in this work to determine the potential pathway that achieve the maximum economic performance with a minimized environmental impact simultaneously. This will also present an optimization approach to design of the uncertainties in the form of the multiple feedstock supply and product demand scenario. Process graph can effectively examine the what-if scenario and conduct the sensitivity analysis. So recommendation in this project, the proposed approach can be easily devised and formulated to handle the possible uncertainties that can arise from the advancement of technologies and market price. So the process graph can be further supplemented by the multiple programming. So thank you. This is